So, what is C2V? C2V has symmetry which involves C2. C2V has elements identity C2, then C2, then sigma V and C2 sigma V, right. Essentially it is made of E and C2, right, and you take a product with sigma V with that, right. You take it as a product with E and sigma V. So, this product also turns out to be a direct product in the context of C2. Why? You can show that whether you write C2 sigma V, you can show that it is same as sigma V C2. Clear? V is the vertical mirror. Sure, all of you have synced the notation following the earlier lectures. Absentees or miss some lectures, you should please go back, look at the previous lectures, otherwise the notations will be continuous, like whatever I have followed in the previous lecture will continue. Okay, I am not going to specifically again define the notation. So, the vertical plane mirror, the operation is commuting. So, this commuting property will imply that it is a direct product. Okay. So, this is a direct product group. This will not continue when you do it for C3V. This also I spent lot of time in the class. Still I see lot of errors in the paper. So, C3V, what are the elements? Identity, C3, C3 squared, sigma V C3, sigma V C3 squared. Okay. You can write the elements as if you are doing E C3 and C3 squared, you can multiply with E and sigma V. Okay. But you can show that C3 sigma V is not equal to sigma V C3. Okay. So, which means the C3V is not a direct product. Okay. Clear? So, if C3 sigma V is same as sigma V C3, you would have got C3 equal to, C3 is like a self conjugate element, right. You could have, but now you also know, because this is a bilateral axis, C3 is a bilateral axis. Whenever you have a mirror containing the axis, you know that C3 K sigma V will give you C3 minus K. This also implies C3 and C3 inverse, which is nothing but C3 squared, belong to the same conjugacy class. So, this is true for a principal axis which has a vertical mirror plane, then it becomes the bilateral, and you can use the condition that the conjugation sigma V inverse is same as sigma V, the conjugation will take the element to the inverse of the element. So, that is why C3 and C3 inverse belongs to the same conjugacy class. Using this also you can show sigma V C3 is okay. So, this is another way of validating that it is not equal to this is not equal to this. Once it is not equal, order matters, then this direct product which I am writing, like I can find the elements by using this, okay. That set will be a complete set whichever order you take, but the claim to be a direct product group is that you have to get the same element whether you do C3 with sigma V or sigma V with C3. Okay. If that is not happening, it is not a direct product group. In fact, you can show this to be a semi-direct product. This also we discussed. How did we discuss? We said that this is like a symmetric group, right, of degree 3, it is isomorphic to it. This group is isomorphic to this, and then in that symmetric group you can have alternating group which is a subgroup. This is a subgroup of the alternating group is a subgroup of the symmetric group, and the elements of this are nothing but the 3 cycle which has even permutations, right. Am I right? If you remember, the elements here will be E 1 2 3 1 2 3 squared, and that is isomorphic to E C3 C3. So, you can show this to be a semi-direct product of, what is the notation? This is the way we write, and times the okay. So, the 3 elements will get multiplied with this, and that is a semi-direct. This also we discussed. Okay. So, the next thing which we were trying to write is a matrix representation. I said let us do a matrix representation where we take x, y, z and operate C2 on this. You will get x prime, y prime, z prime, and you can write the 3-dimensional representation. So, that is being displayed on the screen. So, C2 will be what? It will be taking x2 minus x, y2 minus y, because it is 180 degree rotation, z to z. So, you will have minus 1 0 0, okay. That will be your C2. So, as shown in the screen, I have put it in identity element is identity. Looking at the how it operates on your x, y, z components of your position vector, C2 will be the diagonal elements, x component will be minus x, y component will become minus y, and z will not change. If you do the mirror, just the mirror, if you take the mirror to be in the xz plane, which components will not change sign? A mirror in an xz plane will not change x component or the z component, but the y component will change sign. Clear? And similarly, C2 sigma v can be written as if it is a mirror in the yz plane, both are equivalent. So, the mirror in the yz plane will change the x component alone, but not the y components and z component. Is this clear? How I have written a matrix representation for the C2V group? I have tried to find the same, these matrices when you multiply, it will satisfy the same multiplication table. Okay, matrix multiplication, if you do, the multiplication table of C2V will be satisfied by these 3 cross 3 matrices. Clear? Okay. So, now what you see here is that these are already diagonal. Okay, this is what you see here. But if you had done a 120-degree rotation, that also we did in class, right. So, if you want to write C3 element, it will be cos 120. What is cos 120? So, this will be the matrix which you will have to write, right. Cos 120 is sin 30, right, sin 30 is half, and then minus half, this one will be root 3 by 2 okay. So, it is already in a completely diagonal fashion there, but here you see something where it is a block diagonal fashion. Okay. So, that is the first observation. C2V, all the matrix for all the elements, there are 4 elements in C2V, all the 4 elements are diagonal. And C2V is also an abelian group or a non-abelian group. The direct product groups, each one is abelian, the product is also abelian, so it is an abelian group. C3V is isomorphic to the symmetric group of degree 3, which is a semi-direct product, and we have seen many times that it is not an abelian group. Okay. So, I am just taking these 2 simple examples. Whatever I am doing for the simple examples, you can extrapolate for other groups. Okay. So, it is completely diagonal, and we saw this definition of what is reducible and irreducible representation is what is my aim today. Okay. So, instead of working with x, y, z basis, so this one is acting on x, y, z, giving you x prime, y prime, z prime. Okay. And you see that the z component is never changing. You could also work with these matrices acting on the xy plane. Okay. So, you can do things like what is the C3 maxes which takes xy to x prime y prime. That is nothing but this 2 by 2 block. Okay. If you just take the 2 by 2 block, you can say they are 2 dimensional matrix representations for the same group. Which group? Symmetric group of degree 3 or C3V. This is one element I have written. You can write it for sigma V also. You can write it for C3 times sigma V. You can start writing those matrices. Right? How will you write C3? Sigma V is what? So, let us take the sigma V to be the yz plane, for example. If suppose I take the yz plane, then this is supposed to give me and y, right. And then write the matrix form for this. So, the matrix form for this will be x goes to minus x, y remains same, and this is a 2 by 2 matrix, sorry. This is a 2 by 2 matrix which you have to write, and this is a 2 dimensional representation for the sigma V, and if you want to find C3 times sigma V, you just multiply. You can do the multiplication and write what happens. Similarly, you can write C3 squared times sigma V, and you can write all the matrix elements. You can write the 2 cross 2 matrix elements. So, this will be 1 0 0 1, this will be minus 1 0 0 1, but then there are elements which are minus half, root 3 by 2, minus root 3 by 2, minus half for this. and that will be the inverse element which is like rotating by minus 120 degrees, right. So, you can write all the matrices which acts on the xy coordinates alone, and it gives you another representation which is a 2-dimensional representation for the C3V group, correct. Why it is a representation? The product of this with this will give me identity. I can see that the multiplication table is satisfied by this matrices. Okay. So, in that sense it is a 2D representation. Can I say whether this 2D representation is reducible or irreducible? That is the next question. Okay. What is the definition of a given matrix? If I give you a matrix, you have to see whether it is reducible or irreducible. First of all, you have to find, so can we find a matrix S such that you can further break it into. So, if it is 2 dimension, I should see whether there is a matrix S, let us take half, I think this is plus, right, S inverse, it is 2 dimension. Can you break it up into a 1 cross 1 and a 1 cross 1? Okay. Suppose you find the matrix S which breaks it into 1 cross 1 and 1 cross 1. What will happen to the identity element? Identity element will not be touched, right. Identity element is already in a complete diagonal form. So, this S which, if suppose it diagonalizes it, it will automatically diagonalize this as well as probably this, right. It is not really going to matter. What can matter is the other elements. Can all the elements be diagonalized by the same S matrix, the same S elements? Okay. If suppose you find the S, so find S, then check S sigma V C3, I am not writing the matrix, you write the 2 cross 2 matrix here. Whatever 2 cross 2 matrix you find here, you put the same matrix S inverse question mark. Can you make it into a diagonal form? By this I mean the off diagonals are all zeros, okay. That is the meaning of writing it in this shorthand notation. Yeah, in this case of 2 cross 2, there is nothing called block diagonal, but in general if you had a 3 cross 3 or a 4 cross 4, you could break it up into sub pieces, okay. So, in this particular example of a 2 cross 2 matrices, can you find an S matrix which simultaneously the similarity transformation with this S matrix on all the elements should give me diagonal matrix? Can you achieve it is the question. I am telling you the answer is no, okay. One is you can do it by brute force and check it out. I am trying to tell you that simultaneously making all the elements to be diagonal, starting with this 2-dimensional representation, is not possible, okay. So, one is to do it by brute force, another one is to try to understand from a set of lemmas, theorems and postulates, but as a to get a feel for it, please try it out. I would ask you to, I would strongly urge you to try out doing this, find an S first. This diagonalization is trivial for you, you can do it, After you do that and find the S, I am sure all of you have done diagonalization of matrices. After you find that S, try to see whether that S when you employ on the sigma 3 V or sigma V C3 or sigma V C3 inverse, check whether what happens. Other two elements are trivial, identity and the other one, but non-trivial elements which involves off diagonal elements, is this same S which you are going to find going to diagonalize it. If you can find that out, then you can say that the two dimensional representation, suppose you find an S, so let me write it. If we find S which diagonalizes all the elements of group G, okay, all the matrix, all the representing. So, let me write it this way. Representation of the elements of group G. Suppose you find an S, and if you take that matrix representation, so let me denote that matrix representation as some n cross n matrix for a group element G. Okay. Suppose you find S inverse, if you can break this into a piece which is n1 cross n1, n2 cross n2 and so on, such that the n1 plus n2 should add up to n, okay, n cross n matrix for every group element. Okay. So, let me call this as, so gamma 1 for the same G, gamma 2 for the same G and so on. So, these are lower dimensional matrices. So, this you should do it for all G. This is not dependent on G, should be the same as on all G. If we find an S which satisfies this, okay, then gamma n cross gamma n of G is reducible. Okay. Yeah, no, given a representation. I am not saying that this gamma. Yeah, so I am just saying in an abstract fashion, take an n cross n matrix representation, take that representation, matrix entries also, and then work it out. If you take another n cross n with some other entries, that is a different story. Okay. So, I am not saying that.
But that is representation independent. If you can find S matrix for one representation, then you can find it for any representation.
It does not depend on the elements of the group. It does not depend on this, but it depends on what is the entries of this matrix. Okay. So, in some simple cases there is only one unique matrix which you can write, but there are some complicated situations where there will be two different 3 cross 3 matrices which you can write. I will come to it, some examples I will tell you, but right now you take that just like this example where I have taken a 2 cross 2 matrix or a 3 cross 3 matrix, you can try to see whether you can find an S which satisfies this. that is another way of arguing it for simple cases. Higher representations also it is possible to argue this way, yeah. Okay, good. So, as he is already saying, but that is not really a postulate because I want to do it in general for a n cross n matrix. What are these blocks in which it can break, that you cannot generally answer from your just an abelian or non-abelian. Okay. So, the question that it is abelian or non-abelian will not really help me, but what I want to drive upon you is that there is going to be some kind of an orthogonality theorem which is called great orthogonality theorem, which plays a crucial role in saying that we can find an S, not that I am going to find the S, but that theorem tells you that yes, I can find an S which does this job, in which case I can say that this one is a reducible representation. If I cannot find an S, yeah, if I do not find an S, if S is not found, then this element itself, what does it mean? If you do not find an S, I cannot break it up like this, which means this one will itself be a irreducible representation. Okay, I am using the shorthand notation REFN, but representation we will start using. Further I will shorten this and call it as irrep. Okay. So, I am only claiming to you that this one is an irrep, this 2-dimensional matrix representation is an irrep, or in other words I cannot find an S which will, block diagonal has no meaning in a 2 dimension, it should become completely diagonal, and one of the ways to see it is that it is non-abelian. You can, so that you can not simultaneously diagonalize all the elements of a non-abelian group, that is another way of arguing. Okay. So, good. Good, but that is what is happening in your, if you see that earlier representation, that is a good point. So, you do see that the abelian is trivially a block diagonal form, and you can pick up the irreducible blocks out of it. Okay. So, here let me also say that if these are what we call it as a irreducible blocks. Representation or irreps. Okay. So, gamma 1, gamma 2 are all different, each of these blocks, block diagonals are called the irreducible representation for the same group. What I mean by that is that you can play around with gamma 1 of G alone and write the group. That is what happens in C2B. In C2B, I can say that 1 minus 1, 1 and minus 1. Okay. So, let me write that here. It is a 1 cross 1 matrix. Okay. So, this is a 1 cross 1 matrix with the elements which is 1, 1, 1 and 1. Will trivially satisfy any group actually. Okay. In fact, here for the C3V you can still take it on the Z axis, E C3 C3 squared sigma V C3 sigma V C3 squared, you can apply it on the Z axis. If you do it on the Z axis, what happens? Identity nothing. C3 also is the Z axis itself. So, here also you can have a representation which is acting on 1-dimensional Z coordinate, correct? And what will that element be? 1, 1, 1, 1, 1. It is a 1 cross 1 matrix, right, because it is acting only on the Z axis. For C2V there are only 4 elements, right. This is for C2V. This is a matrix, 1 cross 1 matrix. 1 cross 1 matrix is just the number 1. It is like a trivial representation which is going to be there for every group. Okay. So, this is a trivial, sometimes called unit representation, irrep for every group. Okay. So, the number of elements is the order, in this case it is 4, this case it is 6. That representation is there.